Welcome to the Explainer. So today we're tackling something that is honestly one of the coolest puzzles in natural language processing. How exactly do language models predict words they have absolutely never seen before? Think about it. If a model has never encountered a specific phrase in its training data, what on earth does it do when that phrase inevitably pops up out in the real world? It's a massive mathematical hurdle for sure, but as you'll see, the solution is an absolute stroke of genius.
Okay, let's dive into this incredibly structured roadmap. We're going to start with the unseen word problem, then unpack absolute discounting, take a look at the infamous Hong Kong anomaly, and finally arrive at Neither-nay smoothing.
Section 1. The unseen word problem.
Standard language models are incredibly rigid. If they haven't explicitly been trained on a specific string of words, say a totally unique bigram, they just assign it a strict probability of 0. Literally 0. But we live in the vast, infinite world of human language. Assigning a 0 probability just because you haven't seen a phrase yet, that is a recipe for a completely broken model. We have to leave some room for the unknown. So the intuitive fix for this is kind of like playing a statistical Robin Hood. We have to discount the counts for the frequent, everyday n-grams in order to save some probability mass for the unseen ones. Basically, we're stealing a little bit of statistical likelihood from the words we see all the time, and we redistribute it to the words we haven't seen yet. But that brings up the big question. How do we decide exactly how much probability to steal?
Let's move to and see how this builds in Section 2. Absolute discounting explained.
To figure out exactly how much probability to Robin Hood away, researchers Church and Gale came up with a partial but hugely influential solution back in 1991. They decided to look at hard empirical data to see exactly how probability shifts between training data and real-world application. So, I want to pose their exact question to you. If a bigram appears exactly 4 times in your training data, how much should we discount it? Well, to figure this out, Church and Gale set up this massive, super clever experiment. First, they built a bigram grammar from 22 million words of AP Newswire text. Then, they took a completely separate, held-out corpus of another 22 million words, and they just checked the real-world counts of those exact same bigrams.
And this brilliantly illustrates the reality of statistical language models. Just take a close look at this table comparing the training set counts on the left with the held-out set averages on the right. If a bigram was seen exactly 4 times in the original 22 million words, you might logically assume it would appear 4 times in the next 22 million, right? But it doesn't. On average, a bigram with a count of 4 originally only showed up 3.23 times in the held-out set. A count of 5 showed up 4.21 times. A count of 6, 5.23 times. Are you starting to notice a pattern here?
The gap is incredibly consistent. Aside from the counts of 0 and 1, we can actually estimate the held-out counts surprisingly well just by subtracting a single fixed absolute discount from the training count. And that magic number is roughly 0.75. So the equation for absolute discounting just subtracts this fixed 0.75 discount from the frequent counts. We trust our high counts enough that subtracting a tiny fraction like 0.75 really isn't going to hurt them, but it frees up just enough probability mass to distribute to the unseen words. It's a seriously elegant solution.
But as we transition into Section 3, the Hong Kong anomaly, I have to warn you, while absolute discounting is clever, it has a fatal, completely context-blind flaw. To understand why we absolutely cannot just stop at absolute discounting, we have to look at what linguists playfully call the Hong Kong anomaly. Take a look at this sentence on the screen. I can't see without my reading blank. I want you to ask yourself, what word does your intuition logically tell you should come next? You're probably thinking glasses, right? Reading glasses. I mean, it makes perfect contextual sense.
Now what's really interesting about this slide is how a standard ununigram model fails just spectacularly here. If we rely on absolute discounting alone, the model only looks at the raw frequency of individual words. The word Kong actually has a massive overall frequency in the training data simply because the phrase Hong Kong appears constantly in news text. Glasses, on the other hand, actually has a lower overall frequency. So a standard ununigram model will wrongly predict I can't see without my reading Kong, just because Kong is a highly frequent word. It completely ignores the fact that Kong almost exclusively follows the word Hong. It has high frequency, sure, but terrible context diversity.
Which brings us to Section 4, Neither-nay smoothing, where our heroes step in to solve this exact anomaly in 1995.
Right, so Klennegerser and Ney stepped in and realized, hey, we shouldn't just be looking at how often a word appears, we need to look at how many different contexts it appears in.
So the core of their solution is this brilliant concept called continuation probability. Instead of asking how likely is this word, we pivot and ask, how likely is this word to appear as a novel continuation in a new unseen context? A word like glasses follows reading, water, sun, wine, the list goes on. It has a super high continuation probability. But a frequent word like Kong, it occurs in basically only one context, right after hung. Therefore, it will rightfully have a remarkably low continuation probability. We normalize this just by calculating the number of different bigram types a given word actually completes.
Knesernet takes our previous logic and rolls it into a beautiful interpolated big-gram equation, which really breaks down into two very logical, simple steps so the math makes intuitive sense. Step 1 is the normalized discount we discussed earlier, taking that fixed amount, like 0.75, away from our known big-gram counts. Then step 2 interpolates this with our brand new continuation probability, weighted by a normalizing constant we call lambda. Lambda takes that exact probability mass we discounted in step 1 and distributes it based on how many different contexts a word historically appears in. And the coolest part is that the algorithm is inherently recursive. It's kind of like a giant puzzle. If you're using trigrams, you back off to bigrams using the continuation counts, and then you back off to unigrams. But what happens when it eventually bottoms out mathematically? Well, at the very end of the recursion, unigrams are simply interpolated with a uniform distribution. And if we encounter a truly absolutely unknown word, usually labeled as UNK with a count of literally 0, it receives a lambda-weighted uniform distribution. The result? No word is ever left with a 0 probability. Every single word has a mathematically justified place. Now, as a quick footnote to this brilliance, I should mention that researchers Chen and Goodman perfected this method later in 1998 with what is now known as modified Knesernet smoothing. Instead of using just a single fixed discount of 0.75, they realized through further study that using 3 distinct discount values, one for counts of 1, one for counts of 2, and one for counts of 3 or more, actually yields the absolute best performance for language modeling.
Ultimately, Knesernet smoothing fundamentally changed how language models understand the unseen. It mathematically proved that a word's versatility is just as important as its raw frequency. Which leaves us with a totally fascinating thought to close this explainer. If our models are designed to learn our contextual patterns this closely, tracking exactly how and where we deploy every single word, what other hidden, subconscious linguistic habits are they picking up from us? Thanks for learning with me today.